Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Every year, the world mines over 900,000 tons of rare earth metals. Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy, that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few percent, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact: just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Bayunobo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Bayunobo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels, all of this requires metals extracted from places like Bayunobo. And the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Bayunobo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure. Conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Bayun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Bayun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Bayun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Bayun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean? And that every slab of marble is a frozen story of life, death, and time. Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom, if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable-stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge: thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, the piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, two main technologies are used: suspension and cable stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, two massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a two-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which, with filigree precision, extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, They are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify, like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials. Every year, over 1 billion square feet of laminate flooring are sold worldwide. We see this covering every day at home, in offices, and even in shopping malls. But few people realize the complex engineering hidden in each plank. Imagine, under a pressure of over 1,000 pounds and at a temperature higher than 400 degrees Fahrenheit, thin layers of paper and resin are transformed into an ultra-durable surface that challenges stone itself. The laminate market is valued at tens of billions of dollars. But behind these numbers is a process that is impressive in its scale and precision. Watch until the end, and you'll discover the secret that your floor is hiding. Laminate, which has become an extremely popular choice for flooring, combines aesthetics, durability, and cost-effectiveness. Its production begins with the careful selection of raw materials and ends with the creation of finished panels, ready for installation. For the manufacture of laminate, 4 main components are used: the substrate, a stabilizing layer, decorative paper, and a protective layer. Each of these elements plays a key role in the formation of the final product. The process begins with the preparation of the core, or the base of the laminate, which is the most important part that provides its strength and stability. This core is made from a high-density fiberboard, known as high-density fiberboard. The production of HDF begins with sawing wood, mainly coniferous species, into small chips. These chips then undergo a steaming and cleaning process to remove foreign impurities. After this, the wood is transformed into fibers using special mills. The resulting fibers are mixed with glue, most often based on synthetic resins, and formed into a thick, soft mat. Next, this mat undergoes hot pressing under a pressure of about 700 pounds per square inch at a temperature of 400 degrees Fahrenheit. This pressing compacts the fibers, forcing out moisture and air, and creates a strong, uniform HDF board. The thickness of such boards is usually from 1/4 of an inch to 1/2 an inch, depending on the laminate class. The quality of the board directly affects the moisture resistance of the finished laminate, its bending strength, and overall durability. The next important stage is the preparation of the decorative and protective layers. The decorative layer is a special paper on which a printed pattern is applied, imitating wood, stone, or another material. This paper is impregnated with melamine resin, which, after polymerization, gives it hardness and wear resistance. The protective or overlay layer is also paper, but it is impregnated with an even greater amount of melamine resin and small particles of aluminum oxide. Aluminum oxide, which is a very hard material, gives the laminate its main property: resistance to abrasion and scratches. The thickness of the protective layer is only a few thousandths of an inch, but it performs a critical function. Both of these impregnated paper layers are dried and stored in rolls until the pressing moment. The third layer, the stabilizing or balancing layer, is placed on the lower side of the base. This layer also consists of paper, impregnated with resin, and serves to prevent the board from warping. Without this layer, during use, the difference in pressure and humidity between the upper and lower layers of the laminate could lead to the panel bending. The stabilizing layer helps to maintain the geometric stability of the board. The key moment in the production of laminate is the hot pressing process, which combines all 4 components into a single monolithic panel. This takes place on multi-layer presses, where the prepared sheets are assembled into a sandwich. First the stabilizing layer, then the core. After that the decorative layer, and on top, the protective overlay. This multi-layer structure is placed in a press, where under the influence of high temperature, which can reach 420 degrees Fahrenheit, and a pressure of 1,200 pounds per square inch, the melamine resins melt and harden, securely bonding all the layers together. This process takes from 30 to 40 seconds, and is called lamination. During pressing, the surface texture is also formed, which can imitate the texture of wood. After pressing, the laminate sheets are cooled and stabilized, which is important to prevent deformation. When the panels have cooled, they are sent for trimming and milling. At this stage, the large sheets of laminate, which can be 8 feet by 4 feet in size, are cut into smaller, standard-sized panels. For example, 48 inches by 6 inches. After trimming, locking joints, known as a click system, are milled on the side edges of each panel. This is a key feature of modern laminate, which allows it to be laid without using glue. The milling process must be extremely precise to ensure a perfect connection between the panels. Tolerances are only a few thousandths of an inch. The final stages of production include quality control and packaging. Each batch of laminate is tested for abrasion resistance, impact resistance, moisture resistance, and other parameters. The abrasion resistance test, known as the Tabor test, determines the wear class of the laminate. A high class means that the laminate will withstand a greater number of abrasion cycles. After successfully passing all tests, the panels are sorted, packed in sturdy cardboard boxes and prepared for shipment. The weight of one box can be 40 pounds. All these processes, from the transformation of wood into fibers to the packaging of finished panels, are part of a highly automated and technologically complex production cycle. The result is a laminate that not only has an attractive appearance, but also high performance characteristics, which makes it one of the most popular flooring options in the United States and around the world. The total length of a production line can reach hundreds of feet, and the production speed is measured in thousands of square feet per hour. Understanding these processes helps to appreciate the complexity and engineering excellence of the product that we see every day in homes, offices, and commercial spaces. The global laminate flooring market has shown stable growth in recent years, driven by its popularity as an affordable, durable, and aesthetically attractive covering. According to expert estimates, it is projected that by 2030, this figure will grow to $35 billion, demonstrating an average annual growth rate of about 4%. The main driving factors are the construction boom in developing countries and the growing popularity of do-it-yourself repairs in developed countries. The geography of production and consumption. The largest regions for laminate production and consumption are the Asia-Pacific region and North America. In the United States alone, the annual production of laminate reaches billions of square feet. Europe also remains a significant player in the market, but the growth rates there are somewhat slower. Approximately 40% of the global demand for laminate comes from the residential sector, while the remaining 60% is from the commercial and industrial sectors. A significant amount of wood raw material is used for the production of laminate. Typically, to produce 1 square foot of high-density laminate board, approximately 0.15 cubic feet of wood is required. Given the production volumes, this leads to significant consumption of forest resources, although most manufacturers use recycled wood or waste from the sawmill industry. Standard sizes of laminate planks in North America range from 48 to 60 inches in length and from 5 to 8 inches in width. The weight of one package can be from 35 to 45 pounds, depending on the thickness and density of the material. In the modern market, there is a growing demand for laminate with a high imitation of natural wood and stone. Over 70% of sales are for decors that imitate wood, with oak and maple shades being the most popular. The demand for water-resistant laminate is also growing, which occupies over 25% of the market and continues to increase its share, especially for use in kitchens and bathrooms. The next time you walk on your laminate floor, remember this epic story. So enjoy your renovated space. Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills, where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, This scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that, at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. a special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles.